Thank you so much, Rudolph. Yeah, and again, I apologize for not being able to be there in person. I wish I could be there in person. It's pretty bad in Pittsburgh because we have lots of snow. There's a snowstorm coming. It's below freezing, and I hear it's really nice. It's really nice there. So let me start sharing my screen. What I'd like to do today is I'd like to give you an introductory overview lecture into deep learning, and we talk a little bit about neural networks, optimization, and such. So some of the resources that I think are really awesome resources for you to look at is I'm going to be borrowing a lot of resources from Hugo Larochelle's class on neural networks. It's an excellent resource. I'll provide the website here. Hugo covers a whole bunch of different topics, and he's done a really fantastic job. I'm relying a lot on, when I'm teaching these classes on his materials. It's an excellent resource. I'm going to be using a lot of it. And there is also an excellent tutorial on deep generative models. If you're interested in those models, we'll cover them a little bit in this tutorial, but also there is an excellent tutorial on that. So what I'd like to do is I'd like to cover a few things in this tutorial. So we're going to go through definition of neural networks. We'll look at some basics of what these neural networks are. We're going to quickly go through the training of these models, look at the loss functions, and briefly look at the backpropagation algorithm. And then we spend a little bit more time on some of the state-of-the-art optimization technique and regularization techniques, such as dropout, batch normalization. And we're going to look at the best practices, how we train these models. And then I'm going to spend a little bit of time looking at convolutional neural networks. So these are specific models that are designed for image processing. And right now, if you go to any computer vision conference or anything that has to do with images, convolutional neural networks are right now state of the art for processing image-like data. And then in the last 10 minutes or so, I'll just give you a brief overview of unsupervised learning or building statistical generative models, because I think that field is becoming very, very popular in the deep learning community. Okay, so let's quickly look at what the neural networks are, and let's look at a very simple definition of artificial neuron. So we basically have the following equations. We have a neuron pre-activation, or we sometimes call it input activation, and this is nothing more than just taking a linear average, linear combination of the inputs, adding some bias term B here. And then we're going to have what we call neuron output activation, which is we're going to take our pre-activation and pass it through some function G, right? And G here is sometimes called the activation function. B is the bias term. Sorry, that shouldn't be convolution there. And W are the parameters of the model. So think of it as, in a simplest form, it almost looks like a logistic regression, right? And so when we think about activation functions, there are different people use different activation functions, nonlinear functions. The most commonly used one is called rectified linear unit. It essentially has this particular shape that you're seeing here. Well, if the pre-activation input is below 0, then the output is 0. Otherwise, it's just a linear function, right? So it's very easy to implement. It's very easy to compute. The other function that's commonly used as well is the sigmoid function. It has that particular form, right? So it's basically, think of it as a squashing function. Whatever the input is to the neuron, the output is going to be a number between 0 and 1. Now, if I think about neural networks, what are neural networks? Well, it's just basically stacking of these neurons together, right? So here's an example of where we have a hidden layer pre-activation. Again, for example, we can take the linear combination of our inputs. We add the bias term. We pass it through nonlinearity, and we can repeat this process multiple times. And at the end, we're going to have an output layer activation function. So O here is going to be the output activation function. So depending what we're trying to model, like if we're doing regression, then maybe the output activation function is going to be identity. So it's just, or if we're trying to do classification, the output function might be a softmax function, right? So if you think about neural networks in general, they're fairly simple, right? It's just a way of taking linear averages, passing them through nonlinearities, taking weighted sums, passing them through nonlinearities, and that's what they are, right? So it's a composition of multiple nonlinearities. Now, when we think about neural networks and what are they doing, just wanted to show you that these models can be quite powerful. So here's an example that's looking at the capacity of neural networks. So let's look at a single layer neural network. We have some inputs. We can think of the first hidden units, think of them as the sigmoid functions or the threshold function. They kind of like trying to partition the space that way, right? But once we go to the second layer, then by combining these two partitions, we can create something that's nonlinear, right? And that gives you the power of neural networks because we can model fairly sophisticated decision boundaries, right? In fact, when we look at even a single neural network, we can partition the space and as I mentioned, model very sophisticated decision boundaries. So here's an example where R region 2 might belong to class 2, region 1 might belong to class 1, but having these nonlinearities, we can carve out and be very precise about modeling our classes and modeling very nonlinear decision boundaries. Now, how do we train these models, right? So let's look at what's the idea behind training these models. When we think about training neural networks, we think about supervised learning. Imagine that we're given a set of labeled training examples. We have some inputs X. Think of them as images. We have some targets Y. You can think of them as classes that we're trying to classify our images to. And what we're going to do is we're going to perform empirical risk minimization. So that's a standard thing that we would do for any machine learning model. So here's empirical risk minimization. So here we have F, which is a nonlinear function mapping inputs to the outputs, and that's going to be parameterized by some parameter theta. Right? So think of it as a multi-layer neural network, just composition of nonlinearities. And L here is going to be denoting our loss function. You can think about loss function as basically telling you how good your predictions are. If your neural networks makes a prediction about what classes you're seeing in the image, the loss function will be basically telling us how good those predictions are or how much penalty we want to give to our model if Y is the correct output, right? And the third piece, which is very important for deep learning and neural networks in particular, is the specification of regularizer. And we'll talk about what that is. We can think about regularizer as a way of trying to reduce perhaps in some way the complexity of our model. And that actually becomes very important for successful training of large-scale deep neural networks. But when we think of it from training neural networks, we just basically invoke the standard empirical risk minimization framework, which is very commonly used in any machine learning algorithm. So there's nothing magical about neural networks in particular. These are just statistical models, and we do empirical risk minimization. Right, so how do we choose the loss functions? As I mentioned, for classification tasks, maybe we're going to be using cross-entropy loss. It's a common thing to do. For regression tasks, we can use squared loss. And for different other kinds of tasks, you can define your own loss functions. Right, so now to train our model, to train our neural network, we basically need the following. As a modeler, you have to specify the loss function. Right, we have to say what is it that we're optimizing. You have to specify a procedure for computing the gradients of the loss function, right, with respect to the parameters of the neural network. So here you're seeing that. And we also have to specify the regularizer, and we have to specify its gradients. Right? Once we define all of these things, then we can do optimization and optimize the parameters of our model. Most commonly used way of optimizing neural networks and deep neural networks and a lot of different algorithms in general is stochastic gradient descent, right? And the idea behind stochastic gradient descent is it's a version of gradient descent, but you can think of it as follows. So we're going to be performing updates after seeing each example at a time. So here's the procedure. Imagine that we have a multi-layer neural network. We have, in this case, let's say L layers. And then for each training example that we get to see, let's say somebody gives you an image and a particular target, a class for that image, what we're going to do is we're going to compute the gradient. And the gradient computation is we have to compute the gradient of the loss function with respect to our parameters of the model. We have to be able to compute the gradient of the regularizer. And lambda here is going to be, you can think of it as a parameter that trades off the loss and how much of regularization we want to add to our model. And then we do the update of the parameters, right? So once we have all of these computations, then we can basically do the optimization. One of the caveats that we see a lot in practice is the specification of the learning rate, because it's very difficult to set it in practice. One other point that I should point out here is that when we compute the gradients of the loss function with respect to the parameters of our neural networks, we're going to be using what's called backpropagation algorithm. Now, backpropagation algorithm is sort of, deriving it is quite involved. You can look online, the references that I provided. But in essence, you can think about backpropagation algorithm as just a chain rule, right? Because what is this function f? This function f, you can think of it as the composition of multiple nonlinearities, right? So by just using the chain rule, it's easy enough for us to compute the gradients of this function, our output of the neural network with respect to the parameters. Now, how would we set the learning rate in practice? Right, that's actually one of the bigger challenges for training these models. And in practice, there is a joke that goes around that basically says that your learning rate should be 0.01 or it should be 0.001. Right? So generally, one of those two values actually work reasonably well. Now, instead of using stochastic gradient descent, in practice, we actually are going to be using mini batches. And so the idea behind mini batches is that instead of using one example to update your model parameters, you're going to be using mini batch of examples. And the gradient is going to be the averaged regularized loss for that particular mini batch. So think about taking 100 examples, computed the gradients for these 100 examples, and then averaging over those. It's more accurate estimate of the gradient, but the reason why in practice people tend to use mini batches is because you can leverage matrix operations. Particularly if you're using GPUs compute and leveraging matrix operations basically is much more efficient. Right? So instead of taking one example or two examples, basically the cost, the compute is about the same as having 100 examples or 200 examples. Right? So that's important piece. The other very important piece is the use of momentum when we do optimization of these models. So the momentum, the idea behind momentum is we're going to be using an exponential average of the previous gradients. Right? So let's look at this equation here. We compute the gradients of our loss function with respect to our parameters of the neural network. And then we're going to be adding beta, which is another hyperparameter, plus the weighted average, exponential average of the previous gradients. Right? And what it allows us to do is it allows us to pass sort of flat regions in our optimization landscape much more quicker by sort of gaining the momentum. Right, so that's actually turns out to be a really important piece when you're doing optimization. In fact, most of the in practice, in academia, in industry, most of the systems what you're training, and we're going to look at some of the larger scale systems, this becomes very important. Right, so if you're reading a paper that introduces a new technique, a new optimization technique, but doesn't compare to using stochastic gradient descent with momentum, something is wrong, right? Because it's actually very hard to beat stochastic gradient descent with momentum. Now, how do we adapt the learning rates? Or how do we actually choose what the right learning rates to use? And this is another fascinating area of research. It started back in 2011 by introduction of so-called Adigrad algorithm. You can think of the algorithm as the following. You're basically saying, why don't I scale my learning rates by the square root of the cumulative sum of the squares of the gradients, right? So you can think of it as basically saying, why don't I compute the variance of my gradients? And the intuition is the following. If the variance of your gradients is high, maybe you should reduce the learning rate. That's exactly what this equation is saying. Or if the variance of the gradients is small, maybe you should increase the learning rate, right? So intuitively, it should make sense. It's essentially saying, if my gradients go all over the place and they change a lot, maybe my learning rate should be smaller. But if my gradients don't change a lot, right, the variance is very small, then maybe my learning rate is too little because they don't change that much, right? So maybe I should increase my learning rate. And there's a nice theory behind, these types of algorithms. There is also an algorithm called RMS prop. So instead of using a cumulative sum, using exponential moving average, so you take basically exponential moving average of the squares of the gradients. And now probably state-of-the-art algorithm for choosing, for doing optimization and choosing the learning rates is the Adam algorithm. So if you look at most of the recent papers, people would say we optimize our neural networks using Adam algorithm, and it's essentially a way of combining RMS prop with momentum, right? And this is sort of, again, a state-of-the-art for doing optimization with for pretty much any deep neural network. Right, so now let me show you a few examples of regularization, because I think those examples also, those techniques make a big difference for training these models. So one of the commonly used regularizers is L2 regularization, right? And so sometimes it's called weight decay. In the case of, if it's a linear model, it's called ridge regression. And the idea here is you're basically looking at the sums of the squares of your weights in your model, right? So it's essentially saying shrink all of my weights towards zero a little bit. There is also L1 regularization that penalizes the sum of the absolute values of your parameters, and that tends to produce sparse parameters in your neural network. And so these are kind of like commonly used ones. Now, one of the ideas that came in 2014 that has sort of become the state-of-the-art for doing regularization is the idea of dropouts. And the idea behind the dropouts is you basically want to cripple your neural network by removing hidden units stochastically. So the idea is extremely simple. What you do is you basically set each hidden unit in your neural network to 0 with probability 0.5, right? And the idea by doing that, because you're doing it randomly, the idea here is that hidden units cannot co-adapt to other inputs. So it cannot basically say, well, if this input takes this value, if this hidden unit takes this value, and this other hidden unit takes this value, then my class should be 2, for example, right? It cannot do that, because at any point in time, any of those units can just be set to 0. So it has to learn features that are generally more useful, right? And it turns out, you can also use a different dropout rate, but the dropout rate of 0.5 usually works quite well. In fact, I remember when we were publishing this paper back in 2014, we thought about what dropout probability to use, and if you had to choose a number between 0 and 1, you would choose 0.5, right, to sort of not get the criticized by reviewers, right? Because if we choose a dropout rate of 0.2562, then obviously that would raise a lot of concerns, right? So that's, and in general, 0.5 works reasonably well. But again, that's another hyperparameter that you can choose. Now, the fact, one of the interesting things about dropouts is its ease of implementation. So easy to implement that became basically, heavily used in practice because it's very easy to implement. I think in your MATLAB code, it requires a single line change. When your Python code, it only requires a single line change to implement dropout, right? And the idea is the following. You're basically going to be using random binary mask M. Now, for every single, again, this is just the compute of how we do computation in neural network, right? We take our hidden units, or maybe the input, we multiply it by matrix W, we pass it through nonlinearity, and so forth. And the idea is just basically taking element-wise multiplication between your hidden layer activations and just basically randomly setting some of them to 0. And what's more interesting is that the changes to the backprop algorithm are basically non-existent, right? It's literally just changing this line in your code, and your backprop is basically going to be working because the corresponding elements of H are going to be set to 0 anyways. So I think that, dropout became so popular and people are using it primarily because it's so easy to implement, and it works really, really well. At test time, we're going to be replacing our masks by their expectation. So this is just a simply constant vector 0.5 if you're using dropout probability of 0.5. So at test time, it's very easy, again, to implement. And it beats regular backpropagation on many different data sets, and it's basically becoming state-of-the-art technique. If you look at most of the recent work on how people train neural networks, pretty much every single training procedure is using dropout. It's a very good way of regularizing your neural network. There is also some research into what does this mean? What is it exactly doing? One version of it is that you can be viewed as a geometric average of exponential number of networks, right? So every time you drop out certain units, it creates a neural network. And when you're averaging those two in expectation, that's essentially what you're doing. There's also some connections to the Bayesian neural networks and kind of like dropouts characterizing uncertainties and so forth. Right? The second particularly important point that I want to make here is the batch normalization. That's another technique that heavily used right now for making these models train and achieving state-of-the-art results is the use of batch normalization. So the idea is that back in the 90s, Jan LeCun noticed that normalizing the inputs will speed up training, right? So for example, you normalize your inputs to be 0 mean variance 1. Typically, it's an easy optimization problem. And the question is, could normalization be useful at the level of hidden layers, right? At the layer of hidden units? Can we somehow do normalization within each layer? And in 2015, Yoff and Szedi introduced batch normalization, which is a very beautiful technique. And the idea is, again, it's very simple. The idea is that each hidden unit pre-activation is normalized, right? So when we look at the pre-activation function, we want to basically normalize it to be 0 mean variance 1, right? And so during the training, we compute the mean and standard deviation for each mini batch. We subtract mean, divide by standard deviation, basically meaning that whatever goes into my hidden unit has always 0 mean variance 1. And this is super important because it basically avoids regions, the saturation regions, right? Because if the total input to a particular unit is, 1,000, and you're passing it through the sigmoid or through the ReLU, your units basically saturate, right? Or become very large. So optimization becomes an issue, right? And the idea here is that, again, backpropagation takes this normalization into account, and at test time, there's a way of computing the mean and standard deviation, right? And and again, as I mentioned before, it's very important to do this normalization because it keeps pre-activation in a non-saturating regime, and it really helps this big problem. It's called vanishing gradient problem, right? Because if your units saturate, optimization becomes problematic. Your gradients become close to 0, so it just becomes a really, really hard optimization problem. And I think that that was one of the reasons why people couldn't train these deep multi-layer neural networks for a long time, because of this vanishing gradient problem. But batch normalization to some extent fixes it. And the entire algorithm sort of looks like this. You basically compute the mean, you compute variance, you subtract the mean, divide by the variance. There is a certain epsilon factor that makes sure that it's not underflow and overflow and so forth. Numerical stability, but it actually turns out that this factor also makes a big impact on your optimization. And then you basically rescale your pre-activations, right? And you're also learning these linear transformations to adapt to nonlinear activation function, right? So, so that's basically the idea. And so these are the two key points that I want to make, actually 3 points that I want to make, is that using stochastic gradient descent with momentum is important, using dropout, and using batch normalization. So when you put all of these 3 pieces together, that's what basically makes training these deep neural networks successful, right? If any of them is missing, it's probably going to be much harder for you to optimize these models. Okay. Now let me just tell you a little bit about what is the overall training protocol. So you're training your model. Typically, you would train your model on a training set. Right, so think about having a large scale or not a large scale training set. You train your model, you do model selection on the validation set, and this is where you're searching for how many hidden layers you would want to have. What's the learning rate? How many iterations you want to be doing optimization? Right, when you're doing momentum, what's the exponential moving average coefficient there? Right, and so there's a bunch of different hyperparameters that you have to choose, and then you estimate your generalization performance on the test set. And generalization is really the ability or the behavior of the model on unseen examples. We want to be able to do well. We want to be able to classify new images, and we want to be able to classify new speech signals and whatnot. And so the other thing that's commonly used in practice to avoid overfitting is early stopping, right? And here's kind of the intuition what the early stopping is when you look at the number of training epochs as you're training your model, this is what your training curve would look like. And in the traditional textbook machine learning, you would basically see validation error to sort of do this, right? At some point, validation error will start increasing, and then you basically say, well, maybe we should stop over here, right? Now, in practice, what actually happens is that, you know, your training error goes down, but then your validation error sort of like keeps going down. And, you know, if you look at this gap between the training and error and this gap between the training and error, you know, this gap might increase, but at the same time, you know, validation error still goes down. So maybe it still is a better model. And there is a lot of recent work just in the last few years on so-called implicit regularization. And the idea is that we don't have a very good understanding. So it's not like textbook regularization. We don't have a really good understanding of those effects. So it seems that optimization plays a crucial role in generalization. So optimization now, what algorithm you use and how you're using actually impacts your generalization performance. So it's not controlled in many cases by network size, which is, you know, you think about, you know, trying to look at the capacity of your neural network, but rather by some other implicit control, like exactly how using stochastic gradient descent and you know, exactly what kind of randomness you're injecting and dropout and so forth, right? So there is an excellent work that I wanted to point you to, Becknam's work, his PhD thesis. He sort of explores these different ways of these implicit regularization techniques. And really we can think again as optimization as part of regularization and as part of generalization. And so there's lots of open research areas is trying to figure out what's going on with these models. Now, when we think about what's the best in practice, how do we actually do it? You know, think of it as an engineer sitting in a big IT company, or you're trying to achieve state-of-the-art in some new data set. The idea is the following. Given some data set D, you pick a model so that you achieve zero training error. So think of it as completely overfitting on the training set, right? That allows you to do two things. It allows you to check that your code is correct, because at least you can overfit on your training set. And it also allows you to at least figure out what's the largest capacity of the model so you can perfectly fit your training data. And then you basically regularize your model, right? Typically you'd regularize your model using Dropout, you'd regularize your model using L2 regularizers, and so forth. And then you know, there are sort of other things to do. There is initialization plays a very important role. So, for example, you'd want to initialize your weights, your parameters, so that each feature across layer, each hidden unit across layer has similar variance, trying to avoid units in saturation. And again, batch normalization helps with that. And basically, stochastic gradient descent using mini batches with momentum, batch normalization, and dropout usually works really well. Right? I think that that's kind of a de facto a way of training these models. And so this is kind of like becomes a vicious cycle, because what ends up happening in practice is that if I give you even a bigger data set, then I'm going to be building even a bigger model and try to regularize it. You know, you give me a data set that's on the order of magnitude larger, then I'm going to try to build a model that's an order of magnitude larger, and I'm going to be regularizing it, right? So it's kind of empirically, this is what's happening in practice. Now, let me spend a little bit of time on convolutional neural networks, right? Because I think that and give you intuitions about what these are. Convolutional neural networks are basically instances of neural networks, but they have very specific inductive biases and very specific architectural choices. So let's look at specific problem of computer vision, right? So given an input, I'm trying to classify, is it a sunflower, or, you know, is it a dog or a cat? Let's just look at the object recognition as a problem. Right? So we have to design neural networks that specifically kind of design for these types of problems. Right? We want to be able to handle high dimensional inputs. If we have, you know, 150 by 150 image and 3 channels, then we're going to end up with 22,000 pixels. That's a lot of inputs to process. We want to be able to exploit 2D topology of the pixels, and we want to be able to build some invariances. Right? So for example, translation invariance. If I take my sunflower and I move 5 pixels to the right, I still want to be able to say it's a sunflower, right? And so convolutional neural networks are basically largely leveraging these ideas. And there are several ideas, and I listed 4 ideas. There's local connectivity, there's parameter sharing, there's convolution, and then there's pooling and subsampling. So let's quickly go over those. So local connectivity, the idea of local connectivity is basically we only want to connect each hidden unit to sub-region or a patch in the inputs, in the input image, right? So here I'm showing you a fully connected, if we used fully connected neural network, if we have 200 by 200 image, we would basically, in, you know, maybe 40,000 hidden units, we would end up with like 2 billion parameters. It's just way too many parameters to fit. On the other hand, you know, if I restrict, have only local connectivity, looking at 10 by 10 patches, then I would reduce the number of parameters drastically, right? I would only have 4 million parameters. Parameter sharing is another idea. So what we're going to be doing is we're going to be sharing the metrics of parameters across units, right? So in units within each feature map, like here you're looking at the blue feature map and red feature map, are basically sharing the parameters, right? So they're basically covering different positions in the image, but they use the same parameters. You can think of them as using the same filters or the same weights, right? Local patches. And so that's kind of like another important piece. And the third piece is the convolution, right? And so, you know, many of you probably who've taken signal processing class would know what the convolution is. There's a proper definition of the convolution. You know, we use discrete convolution. There's a kernel matrix. And again, we can think of a kernel matrix as the W matrix, the weights of your neural network, you know, having local, looking at the local connectivity. So here's just an intuition of what the convolution is doing, right? Given an input image, if I apply this convolution, it's a 3 by 3 kernel matrix, right? So we're doing 3 by 3 convolutions. Essentially, this particular convolution is looking for vertical edges, right? So it's sort of dark on one side and light on the other side. And this is what the output of the convolution would look like, right? And so the idea in convolutional neural networks is that we're going to be leveraging, we're going to be doing these convolutions, but we're actually going to be learning what these little kernel matrices are, right? And these are going to be the weights of a convolutional neural network. So here's an example of what it might look like. Let's say we've learned these little convolutions. These are, I think, 5 by 5 convolutions. So here we have some input image. We do the convolution, so we're basically sliding the same filter across the image. And if we had to, you know, if we use these 4 convolutions, so we use these 4 filters, this is what response would look like. So these would correspond to 4 feature maps, right, of the output of the convolution. And again, the idea is because we're going to form the entire system as just a neural network, we can do optimization of the neural network, and that would allow us to learn what these filters should be. And that's a very important point because, you know, traditionally back in the late 80s, early 90s, people were thinking about what kind of filters we should be using. Should we be using Gabor-like filters? Should we be using some other filters? But the idea behind convolutional neural networks and deep learning in general is that we can learn what these what these filters should be, right? And then the final idea is the idea of pooling. And the idea of pooling is to try to introduce some notion of translation invariance, right? So if I look at my sort of output of my convolution, and then I can just basically say, well, pick a particular region and just take the average or take the maximum, right? So if I take the maximum, it basically means if I have this image of an Einstein move to the right by 3 pixels, the output of this unit will not change, right? Because, you know, the response might change from this point to this point, but the output will not change because if I'm doing max pooling, it's not going to matter where precisely the location of the eyes or the nose is, right? So that's another important sort of idea behind convolutional networks. And if you sort of pull all of these things together, you basically have, you know, the view of the convolutional network. You're given some image. You're doing convolutions. You're computing these feature maps. You can use ReLU nonlinearity and so forth. So at the end of the day, when you look at these convolutional neural networks, right, these are just neural networks, but with a very specific architectural choices, right? Local connectivity, parameter sharing, we're doing pooling, and we're doing convolution, right? Like just sliding it across different parts of the image. And so that's why we can optimize the entire model in an end-to-end fashion. And that's basically what makes convolutional neural networks successful. Now, very briefly, how do we choose architectures? Right, so there's manual things of how do we, there's lots of different hyperparameters, number of layers, number of feature maps, learning rates, and whatnot. We can try to do cross-validation. Most successful techniques are doing some version of grid search. It requires lots of compute. There are some smarter strategies using Bayesian optimization, trying to come up with the right choices of hyperparameters. Actually, choosing your hyperparameters is a really, really important process. Let me show you a couple of how it's important. Back in 2012, there was a paper that basically introduced this showed that convolutional neural networks can be very successful on large-scale classification tasks, ImageNet tasks, and basically beat state-of-the-art by a lot, compared to traditional computer vision systems. So that was kind of a big breakthrough in 2012. And if you look at this particular model, you have a bunch of convolutions, pooling, and fully connected layers and such. And it was trained on the ImageNet dataset that contains 1.2 million images, 1,000 classes, and you would achieve about 18% accuracy. Right? Top 5 error basically means that you pick top 5 classes, and if the correct class is within their top 5, you consider it to be correct. Right? Now, if I remove one fully connected layer at the top, I can reduce basically the number of parameter reduction is by a factor of 16 million. But the performance drops only by 1%. So it's not such a big drop in performance, but I can really reduce the number of parameters of my model. Right? On the other hand, if I reduce some of the convolutions, right? So here I'm basically getting rid of 3rd, 4th, and 6th layers. Then I have 33% drop in performance. So at some point back in 2013, 2014, people started realizing, okay, the depth of the network is quite important. Right, so how do we choose the right architecture? And at a time, people thought, well, 7 layers is a lot. 6 layers is a lot, right? That's just a lot of compute that we're doing. And then in 2014, Google came up with a GoogleNet model, which had like 24 layers, right? So there's a bunch of, and again, it's a convolution, pooling, and so forth. So it's a specific architecture that they designed that showed really good results. Oh, sorry. And beat state-of-the-art, on large-scale vision tasks. And then in 2016, Microsoft came up with another idea. And the idea is to basically, what they've noticed is basically we say, well, as we increase the number of layers in our model, optimization still becomes a problem, right? Because if I look at my training error, I can fit a 20-layer model much better than a 56-layer model, right? And the same thing happens on test. So this is basically telling me that just optimization-wise, there's nothing to do with generalization. Training a 56-layer model is really hard, a really hard optimization problem. So what they've done is they've introduced this notion of residual connection, which is essentially saying, well, just have these additional skip connections. And people knew about skip connections for a long time, but I think this was the first work that showed that they actually work really well. So you basically had these skip connections, which is the identity. So if you have some input X, you can just copy it over here, and then you can also go through the nonlinearities, and your output here is just the sum of the identity plus some nonlinearity. And they've now built these models, which called ResNet type of models, where you have 154 different layers, and that model is now state of the art for a lot of image classification tasks, right? And so this just shows you how evolution of hyperparameters and architecture has been evolving over time. Now, in the last 5 minutes, let me briefly show you a different kind of research direction, which is unsupervised learning. So far we've been talking about supervised learning, right? It's always the case. We have some images. We try to predict some target, right? We go from inputs to the outputs. And let's look at unsupervised learning. So unsupervised learning is a way of basically trying to model the data without actually having targets. So there are non-probabilistic models like autoencoders, sparse coding models, and then there are probabilistic models. Sometimes these are called generative models. And within the generative domain, there are sometimes people call tractable models, like you've probably heard about mixture of Gaussians. There are autoregressive normalizing flow type of models. There are non-tractable models like both machines, variational autoencoders, and then there are an interesting class of models that basically not necessarily look at the density itself, but look at implicit densities, like generative adversarial networks. And I'll quickly, just in the next 5 minutes, show you what these are. But the idea behind building these statistical generative models is that you have some data, think of it as images, you have some model, perhaps some prior knowledge, and then you're trying to model probability distribution of the data. And so you have an image, and you get the probability of that image. Right, and so the idea is that now if we sample from our P, we can generate new images. Right, so that's kind of the setup. And just to show you that these statistical generative models, this is done using generative adversarial networks. You train on these images of celebrity faces, and this is what the model samples look like, which is remarkable, right? If you look at the 4 years of progression, when I was a grad student, this is sort of the faces that we were generating. Now, you know, we can generate these kinds of faces, which is pretty remarkable. We can do things like conditional generations, right? Again, there's no targets here. We're not doing supervised learning. We're not trying to recognize what's in the image, but we're trying to model one image given the other image. So we're converting horses into zebras. We can do style transfer, which is given the input, try to use a different style to regenerate this image. Of course, sometimes there are failure cases like this one. So it's not perfect, you know, so there's still room to grow, right? And maybe just very quickly, I wanted to show you there are two classes of models that have become very popular. There's a class of models called variational autoencoders and generative adversarial networks. And variational autoencoders are kind of, you know, incarnations of Helmholtz machines that were developed by Hinton and his group back in '95. And these are generative models. You have some generative process of generating the data. You have some approximate inference for recognizing what you have, the states of the hidden units. There's also classes of deep Bose machines, which is kind of like undirected versions of them. So there's a bunch of different kind of graphical model inspired systems here. And maybe just to point out, when we think about deep generative models, we think about these models as follows. We have some latent space. Think of it as a white noise or a Gaussian distribution. We have top-down generative model, which is a multi-layer neural network that generates the data. And then there is a recognition model, bottom-up inference, that just basically trying to approximate the posterior over the latent variables given the data, right? So deep generative model, when you think about that supervised learning, statistical generative model, these are nothing more than latent variable models. And we kind of like do proper way of looking for log probability of the data. Right, and we can, these conditionals here are given by deep neural networks, right? And we can kind of like look at the latent variable models. We can maximize the log likelihood objective. We can look at the marginal log likelihood. So they're kind of like involving the general machinery of working with latent variable models, right? So when people talk about deep generative model, which is a hot topic today, these are nothing more than just latent variable models, but where we model these conditional distributions by very powerful, nonlinear deep neural networks, so convolutional neural networks, right? That's kind of what's been happening in the last few years, right? And variational autoencoders are kind of an instance of that, right? Where we have some prior, which is a Gaussian distribution, and then we're trying to generate the data, and the data is given, you know, the mean here is given by deep neural network, right, that we can optimize. And the recognition model is also given by deep neural network. Now, let me skip this slide. This is basically showing to you that we can optimize these models, and we can optimize them using variational bound. There's math behind it, and so forth. But at the high level, there is a way of learning parameters of these models. In the last couple of minutes, I just wanted to mention, you know, there's a class of models called generative adversarial networks. They form as part of the deep generative model, right? So it's the same procedure. We have some latent code Z. We pass it through the neural network, and it generates the data for us. But it's kind of optimizing a slightly different objective function, right? So the generative adversarial network consists of two components. There is a generator that generates the image, and there is a discriminator. And the goal of discriminator is to try to differentiate between true images and generated images, right? And so when we think about optimization for these types of models, you know, the idea is the following. Imagine that I'm trying to optimize my discriminator, and my discriminator outputs 1 if it's a real image, or it outputs 0 if it's a fake or generated image. Right? So I want to train my discriminator to basically say, well, if it was generated by my model, I want my discriminator to be 0. If it's a true image, I want my discriminator to be 1. Right? And the way that we train the generator is basically saying, well, change the parameters of this model. Instead of doing maximum likelihood estimation, change the parameters of this model such that when I pass it through my discriminator says it's a real image. Right? So it's kind of like a min-max objective function. It's a way of optimizing them. And, you know, in the last few years, people started noticing, that these models give really good, strong kind of examples of samples. Like, the first time it came up back in 2015, 2016, you look at the CFAR images, these are samples. Like, if you look at this horse hits, it's remarkable. It's too good to be true, right? Because generating models, images is a really, really hard task. Now, here's some examples of cherry-picked examples of what these would look like. And one of the open research questions today is how can we quantitatively evaluate these models? Are they memorizing? Are they doing something interesting? How well can they generalize and so forth, right? Here's another example of you can adapt these models to dealing not just with images, but you can also deal with point cloud data, right? So here you have adversarial autoencoders, you have point cloud generative adversarial networks, and so forth, right? You can also do interesting things like interpolating between, chairs and tables. So at least this is showing that GANs are probably doing something reasonable because they at least can interpolate, right? They can kind of like take an airplane and move it, or take a chair and morph it into the table. And so I guess on that point, since we're kind of like running close on time, I want to say thank you, and maybe there's some time for questions.